notes today is starting off with what Hess's law is, but then I also have to go over a little bit of what you would need to know for the calculations for the lab activity today and the lab itself next time. I think on this first slide, you don't actually have to write down any of this. Just let me talk through what this is, and then I'm going to kind of show you an example instead. So, not every reaction is as simple as start to finish. If you remember in the kinetics unit, sometimes you could have two steps in a reaction. But when you add the two steps together, that will tell you what the reaction overall is. Remember, you could get rid of a catalyst or an intermediate in those two individual steps. Hess's law is kind of like that, where if I want to know the heat involved for any reaction, if there are multiple steps in order to get to that reaction, I could do a little bit of math if I know the heats for each individual reaction and then add it all up. That would give me the heat for the reaction I'm looking for. It's kind of referred to as the indirect method. Now, if you looked at your goal sheet, it talks about state functions and things like that. And it says, well, you don't need to know what a state function is, although this is an example of it. But again, my first bullet point is just saying that, you know, when reactants turn into products, the heat involved in the reaction is going to be the same whether or not it's one step or several steps. I mean, think about our activation energy curves that, you know, start here, end here, you go up a hill, you go down. If I add a catalyst, it's a smaller hill, but it's still the same start and finish. So typically the direct method is what we learned last time, heat of formation. I have to go over what the indirect method is here instead. What I'd like to show you to maybe make sense of this is I'm going to give you a reminder of redox stuff that we did. So what I'm showing you on the whiteboard right now isn't anything that's actually, you know, on this, but my hope is that this would be a reminder to you of things that we've done similar to this before. It's the oxidation equation of hydrogen peroxide. This is the reduction of the permanganate polyatomic ion. Remember the purple stuff? Hydrogen peroxide, we put them together. Now, when we did this type of stuff in class, what we had to realize is that we needed to cancel out the electrons gained and the electrons lost in order to get our net reaction. Is this all ringing a bell? So my top equation I would have multiplied by 5. My bottom equation I would have multiplied by 2. And then I would have just added the two together. So, again, if I gave you the overall net for this, it'd be 5H2O2 plus 6H plus. Because what would happen is I'd have 10 H pluses from the oxidation equation on the product side. I'd have 16 on the reduction equation, so 6 is my net change. I think a lot of people on a lab quiz got that wrong because they tried to put it on both sides. So we did something similar to what I'm about to show you today with thermo, because what we had to do is use those two coefficients in stoichiometry. But we were given more than one equation and we had to put them together. Sometimes we had to multiply by something to help things cancel out to put them together. I bring this up because this is very similar to what we're doing today. And again, in years past, this has been kind of tricky, so I'm hoping that maybe just that first little reminder of what we've done will help out. Okay, so I'm going to write this up on the smartboard because I didn't feel like actually writing out these equations. It was too much work for me. PowerPoint and subscripts don't work great together. we're going to figure out what is the enthalpy for this reaction shown up on the board. This is the synthesis of pentane. Pentane is C5H12. Now, what if we don't have the heat of formations for the three things and we can't just do products minus reactants? What if instead I give you three separate equations? And again, I'll write them out as an equation form here in a minute. And then we have to figure out how to put these together. What can I multiply these things by to make it look like that? That's what our goal is today. And that goes back to what I wrote up on the whiteboard there of what you are given will determine how you can solve any of these problems. So again, I'll rewrite even these numbers here, so don't worry about catching all of that because it'll be a little bit easier on the smartboard to do. So, the first equation I wrote in there was the combustion of pentane. So that's C5H12 plus 8O2 yields 5CO2 plus 6H2O. And the delta H for that was negative 3,244.8. And the second equation I gave was the synthesis of carbon dioxide, which is just carbon plus oxygen makes carbon dioxide. Delta H for that reaction I gave you as negative 393.5. By the way, it's just the heat of formation for carbon dioxide. If you used that on the website last time. Synthesis of water vapor. 2H2 plus O2 yields 2H2O. And the delta H for that reaction is negative 483.5. If you were given this and then told, so I'll scroll back down in a minute, you want to get to the reaction I first said, 5 carbons plus 6 hydrogen gases makes C5H12. What we can do is figure out how can we manipulate these algebraically to make these three then add together to look like my equation in blue. For example, look at my blue equation, what I want to get to, and look at the first reaction. What I would notice is the thing that they both have in common is the C5H12. Right? However, in this equation, the one that we want, it's on the product end of the arrow. In this equation, it's on the reactant side. We need to flip the equation around. We need to do the reverse reaction. Does that make sense? If the forward reaction is exothermic, the reverse reaction would be endothermic. The exact same value, except for we flip the sign. So in other words, if what I want to do to this equation is basically make it go in reverse, I then need to multiply my delta H by negative 1 to change the sign and make the exothermic turn into endothermic. Okay, equation number 2, the synthesis of carbon dioxide. When I look at this equation, and then I look at my equation in blue, what I notice here is both of them have carbon. However, my equation on the bottom has 5 carbon atoms. My equation on the top only has 1. Just like canceling out electrons and things like that, I need to multiply this top equation by 5. Because if I multiply this top equation by 5, I now have my 5 carbons. But if I have 5 times as much reaction, that's going to give off 5 times as much heat. So I need to multiply that delta H by 5. Lastly, look at the last equation in black versus our equation in blue. The H2 is what they both have in common. So, what do I need to multiply this equation in black by? 3. Which means that if it's 3 times as much reaction, it gives off 3 times as much heat. I need to multiply that by 3. Now, what I'm doing in red, you don't have to do. But what I'm doing in red is to prove something to you, because there was more than just carbon, hydrogen, and pentane in this reaction. When you did redox, after you multiplied equations, you added them all together. Electrons canceled out. The previous problem I showed you, some of the H pluses canceled out. What I'm telling you right now is if you added together these 3 equations, so again, this one which I just showed the reverse for, this one that I multiplied by 5, and this one that I multiplied by 3, the only things that you'll have remaining is the equation we're looking at. I can prove it to you. Look in the first equation. I have 5 CO2 on the reactant side. I have 5 CO2 on the product side. They cancel each other out. I have 6 H2O on the reactant side. I have 6 H2O on the product side. They cancel each other out. I have 8 O2 on the product side. I have 5 plus 3 is 8 O2 there. I'm left with this plus this equals this, which is my equation. What I just showed you, you do not have to do. However, year after year, students are concerned of, do the other things actually cancel out? They always will. If you are given a problem that is a Hess's law problem, they're not going to just throw at you 2 extra equations just to see if they can mess you up. You are given the steps that are needed. What you need to do is recognize in these original 3 equations in black, what do I have to multiply them by? And then you add these numbers up. So I would take the 3,244.8, because I multiplied by -1, and I would add it to 5 times the negative 393.5. And I would add that to the negative 483.5 times 3. And that would get me a delta H overall of negative 173.2 kilojoules per mole. The main mistake I see from students year after year is they do this multiplication that I showed you on the far right-hand side of the smartboard, but then they want to do products minus reactants. But this isn't heat of formation. This is reactions that we are now combining, just like we did when we did our redox. That's why we have to be able to compartmentalize, what am I given? This is the path. What am I given here? This is the path. All I teach is algebra in this class for math, but it's a lot of it, and it's a different type at a different time. So that's really your task, is to know which method to use and when. So, this was actually just one of the problems from the book that I decided to do. Do we have questions on this? Because this is Hess's law. And again, we will have time to practice it later on today. So if you have problems, then let me know. My last two slides then are going to go over a little bit more lab-based stuff. For example, when I'm done here, we are going to get ready to do the calorimetry activity again. And today, we are going to figure out how much heat is involved in dissolving of a solute in a solvent. So heat a solution. At the lab bench, as you can already see, there's jars of a white crystal. It's potassium nitrate. We're going to add that to water. We're going to use calorimetry, or styrofoam cups, and we are going to measure how the temperature changes when you dissolve something in water. Not every solute will respond in a way that's noticeable, but several of them will either generate heat, so they'll give off heat when they're dissolved, or they'll take in heat when they're dissolved. And the reason for this is based upon when you have an ionic compound, a couple of things must happen when it dissolves. If you remember last semester, we drew out what it looks like when they dissolve. So we remember that they dissociate, they separate into their ions. Well, if you're going to separate, that means that you have to put in energy to pull things apart. Because when you have opposite charges that attract, to overcome attraction requires energy. I think I mentioned that last class when I talked about you have to break bonds. You're overcoming attraction. But then, water molecules will naturally surround the ions. That's called hydration. And when that happens, energy is released. So really, it's a balance between the two. If you recall lattice energy, that's the energy needed to separate those ions. We talked about lattice energy when we talked about melting points of ionic compounds. Remember, plus 2s and minus 2s are a greater coulombic attraction. They have a higher lattice energy than plus 1s and minus 1s. Smaller ions have greater energy than bigger ones. So we talked about stuff like that. My second sub-point here is if I want to find the enthalpy for the solution, it's a combination of the lattice energy and the heat of hydration. Now that kind of equation I'm showing you for this second sub-point for lattice energy is not one that you would typically solve for. More, it's a equation for you to think about, in that if today in the lab your delta H is exothermic, it gave off energy, you could figure out which of these two values was greater. The lattice energy, the energy needed to break apart the ions, which is a positive value, or the heat of hydration, which I note is a negative value. Because when things are more stable, they release energy. And most chemical processes are a combination of how much did I put in, how much did I give off. Because an exothermic reaction doesn't mean that you just lost heat. It means that you lost more heat than you had to put in. In combustion reactions, when you light a Bunsen burner, that's exothermic. However, you have to ignite it to start it off. What I'm going to show you is similar to what you're going to be doing in the lab today. I'm going to write on the smartboard an example of sodium thiosulfate. That's the formula for sodium thiosulfate. If I were to add it to water, it would dissolve into 2 Na plus aqueous plus S2O3 minus 2 aqueous. I picked this one as an example because when I put this in water, I actually have to use sodium thiosulfate in a redox reaction whenever we work with halogens. So remember in Chem 1 where you had to wear glasses one time, you couldn't wear contacts, and we did the halogen lab in the fume hood? Then you had this big waste beaker of just disgustingness that you were supposed to go down the drain. This is what I reacted with, and then it'd be safe to go down the drain after a while. But this on its own if I just put this in water, shake it up to dissolve, that beaker starts to feel cold. So it is taking heat from the water into the compound. It's an endothermic reaction. Now, I can mathematically prove this. Because what I can do is if I have an equation and I have appendix 2 handy, I made a few copies as well in the class if we needed to. I can do product heat of formation of Na plus ion, thiosulfate ion minus this. So I actually looked all this up. I could take 2 times negative 240.34 plus thiosulfate is negative 648.5. These are my products minus my one reactant, which is negative 2621. Sorry for the weird looking 6 there. And this would give me 1491 kilojoules per mole, which would show, since it's a positive value, that it's endothermic. So today in the lab, you are going to be taking potassium nitrate and dissolving it in water, so solid turning into aqueous ions. You will use measurements to figure out, based on calorimetry, what would be the enthalpy for that dissolving, the heat of dissolving, but then we can check our answer by doing this as well. So that's really why I wanted to add this slide into our notes, is to show you what you're going to be doing today in the lab, but also this is the same as part 1 of next class's lab. All right, one last slide to bring up. To dilute means to water a solution down. And remember in unit 1 we did one of the units we did M1 V1 equals M2 V2 to show the math behind dilution. Diluting is sometimes going to be exothermic. It's going to give off heat. And as I say here, it depends on the concentration of the substance. But sometimes, if you dilute the wrong thing, it can cause that solution to boil because it's giving off so much heat. In your safety contract, because we all read and studied that really well before we signed, just like you click the box to say I agree to terms. On the back side, it mentions that when you dilute a concentrated acid, you don't add water to the acid. You actually add acid to the water first, because then that heat can spread out to more water and not boil the acid right away. You do as you order, you add acid to water. That's based upon another heat example. That sometimes when you add water to a concentrated acid, too much heat is going to be created. There's not enough water there to absorb that heat to cause it not to get a temperature change that's great. And all of a sudden you have boiling 18 molar sulfuric acid, which is not good. Again, I actually have to deal with this all the time because I buy our acid as the most concentrated versions possible. And typically what I have to do when I dilute so students can use it is I get a bin of ice. I put it in there, and then I put my volumetric flask inside of there. I fill it up halfway with water, and I let that water get nice and cold, and then I add the acid to it. That way, when heat starts generating, and you'll see some of the ice melt. I remember one of the first interactions I had, I think with Mr. Butters when he first started here, is like, before school year started and I was preparing a lab, I just asked him, hey, I need someone in here while I'm doing this. Because it is pretty harsh stuff when you're taking the most potent stuff and trying to water it down. You see bubbles every now and then, and it's a little shaky there because of this heated dilution idea. Again, I have no math to supply with this because this is more of a concept to be aware of. However, hopefully on the first couple of slides you saw some calculations that might help you all.